A drilling rig is a machine which creates holes in the ground. Drilling rigs can be massive structures housing equipment used to drill water wells, oil wells, or natural gas extraction wells, or they can be small enough to be moved manually by one person and are called auger sample subsurface mineral deposits, test rock, soil and groundwater physical properties, and also can be used to install subsurface fabrications, such as underground utilities, instrumentation, tunnels or wells. Drilling rigs can be mobile equipment mounted on trucks, tracks or trailers, or more permanent land or marine-based structures. The term rig therefore generally refers to the complex of equipment that is used to penetrate the surface of the Earth's crust. Drilling rigs can be small to medium-sized and mobile, such as those used in mineral exploration drilling, blast hole, water wells and environmental investigations. Large and capable of drilling through thousands of meters of the Earth's crust. Large mud pumps circulate drilling mud through the drill bit and up the casing annulus, for cooling and removing the cuttings while a well is drilled. Hoists in the rig can lift hundreds of tons of pipe. Other equipment can force acid or sand into reservoirs to facilitate extraction of the oil or natural gas. And in remote locations there can be permanent living accommodation and catering for crews. Marine rigs may operate many hundreds of miles or kilometers distant from the supply base with infrequent crew rotation or cycle. Petroleum drilling industry. Oil and natural gas drilling rigs are used not only to identify geologic reservoirs but also to create holes that allow the extraction of oil or natural gas from those reservoirs. Primarily in onshore oil and gas fields, once a well has been drilled, the drilling rig will be moved off of the well and a service rig that is purpose-built for completions will be moved onto the well to get the well online. This frees up the drilling rig to drill another hole and streamlines the operation as well as allowing for specialization of certain services, that is, completions versus drilling. Water well drilling. New portable drill cat technology uses smaller portable trailer-mounted rigs with shorter 10-foot drill pipe. The shorter drill pipe also allows a much smaller mast. Portable trailer-mounted drilling rigs have drill ratings from 300 to 800 feet depending on mud pump flow and pressure ratings and drill pipe sizes. Other, heavier, truck rigs are more complicated, thus requiring more skill to run. They are also more difficult to handle safely due to the longer 20 to 30-foot drill pipe. Large truck rigs also require a much higher overhead clearance to operate. Large truck drills can use over 150 US gallons or more of fuel per day, while the smaller deep rock-style portable drills use a mere 5 to 20 US gallons of fuel per day. This makes smaller, more portable rigs preferable in remote or hard-to-reach places, and are more cost-effective in this new era of high fuel prices. Mining drilling industry. Mining drilling rigs are used for two main purposes. Exploration drilling, which aims to identify the location and quality of a mineral, and production drilling, used in the production cycle for mining. Drilling rigs used for rock blasting for surface mines vary in size dependent on the size of the hole desired, and is typically classified into smaller pre-split and larger production holes. Underground mining uses a variety of drill rigs dependent on the desired purpose, such as production, bolting, cabling, and tunneling. History. Until internal combustion engines were developed in the late 19th century, the main method for drilling rock was muscle power of man or animal. The drilling of wells for the manufacture of salt began by the Song dynasty in China. The well had a particularly small mouth, as small as a small bowl. Archaeological evidence of the drilling tools used in deep well dwelling are kept and displayed in the Zhejiang Salt Industry Museum. According to Salt, A World History, a Qing dynasty well, also located in Zhejiang, continued down to 3,300 feet, making it at the time the deepest drilled well in the world. Mechanized versions of this system persisted until about 1970, using a cam to rapidly raise and drop what, by then, was a steel cable up to 3 m. In the 1970s, outside of the oil and gas industry, roller bits using mud circulation were replaced by the first pneumatic reciprocating piston reverse circulation drills, and became essentially obsolete for most shallow drilling, and are now only used in certain situations where rocks preclude other methods. RC drilling proved much faster and more efficient, and continues to improve with better metallurgy, deriving harder, more durable bits, and compressors delivering higher air pressures at higher volumes, enabling deeper and faster penetration. Diamond drilling has remained essentially unchanged since its inception. Mobile drilling rigs. In early oil exploration, drilling rigs were semi-permanent in nature and the derricks were often built on site and left in place after the completion of the well. In more recent times, drilling rigs are expensive custom-built machines that can be moved from well to well. Some light-duty drilling rigs are like a mobile crane and are more usually used to drill water wells. Larger land rigs must be broken apart into sections and loads to move to a new place, a process which can often take weeks. Small mobile drilling rigs are also used to drill or bore piles. Rigs can range from 100-ton continuous flight auger rigs to small air-powered rigs used to drill holes in quarries, etc. These rigs use the same technology and equipment as the oil drilling rigs, just on a smaller scale. The drilling mechanisms outlined below differ mechanically in terms of the machinery used, but also in terms of the method by which drill cuttings are removed from the cutting face of the drill and returned to surface. Drilling rig classification. There are many types and designs of drilling rigs, with many drilling rigs capable of switching or combining different drilling technologies as needed. Drilling rigs can be described using any of the following attributes: by power used, mechanical. The rig uses torque converters, clutches, and transmissions powered by its own engines, often diesel, electric. The major items of machinery are driven by electric motors, usually with power generated on site using internal combustion engines. Hydraulic. The rig primarily uses hydraulic power. Pneumatic. The rig is primarily powered by pressurized air. Steam. The rig uses steam-powered engines and pumps. By pipe used, cable. A cable is used to raise and drop the drill bit. Conventional. Uses metal or plastic drill pipe of varying types. Coil tubing. Uses a giant coil of tube and a downhole drilling motor. By height, rigs are differentiated by height based on how many connected pipe they are able to stand in the derrick when needing to temporarily remove the drill pipe from the hole. Typically this is done when changing a drill bit or when logging the well. Single. Can pull only single drill pipes. The presence or absence of vertical pipe racking fingers varies from rig to rig. Double. Can hold a stand of pipe in the derrick consisting of two connected drill pipes, called a double stand. Triple. Can hold a stand of pipe in the derrick consisting of three connected drill pipes, called a triple stand. Quadri. Can store stand of pipe in the derrick composed of four connected drill pipes, called a quadri stand. By method of rotation or drilling method, no rotation includes direct push rigs and most service rigs. Rotary table. Rotation is achieved by turning a square or hexagonal pipe at drill floor level. Top drive. Rotation and circulation is done at the top of the drill string, on a motor that moves in a track along the derrick. Sonic. Uses primarily vibratory energy to advance the drill string. Hammer. Uses rotation and percussive force, by position of derrick. Conventional. Derrick is vertical. Slant. Derrick is slanted at a 45-degree angle to facilitate horizontal drilling. Drill types. There are a variety of drill mechanisms which can be used to sink a borehole into the ground. Each has its advantages and disadvantages, in terms of the depth to which it can drill, the type of sample returned, the costs involved and penetration rates achieved. There are two basic types of drills: drills which produce rock chips, and drills which produce core samples. Auger drilling. Auger drilling is done with a helical screw which is driven into the ground with rotation. The earth is lifted up the borehole by the blade of the screw. Hollow stem auger drilling is used for softer ground such as swamps where the hole will not stay open by itself, for environmental drilling, geotechnical drilling, soil engineering and geochemistry reconnaissance work in exploration for mineral deposits. Solid flight augers. Bucket augers are used in harder ground construction drilling. In some cases, mine shafts are dug with auger drills. Small augers can be mounted on the back of a utility truck, with large augers used for sinking piles for bridge foundations. Auger drilling is restricted to generally soft unconsolidated material or weak weathered rock. It is cheap and fast. Percussion rotary air blast drilling, RAB drilling is used most frequently in the mineral exploration industry. The drill uses a pneumatic reciprocating piston-driven hammer to energetically drive a heavy drill bit into the rock. The drill bit is hollow, solid steel and has 20 thick tungsten rods protruding from the steel matrix as buttons. The tungsten buttons are the cutting face of the bit. The cuttings are blown up the outside of the rods and collected at surface. Air or a combination of air and foam lift the cuttings. RAB drilling is used primarily for mineral exploration, water bore drilling and blast hole drilling in mines, as well as for other applications such as engineering, etc. RAB produces lower quality samples because the cuttings are blown up the outside of the rods and can be contaminated from contact with other rocks. RAB drilling at extreme depth, if it encounters water, may rapidly clog the outside of the hole with debris, precluding removal of drill cuttings from the hole. This can be counteracted, however, with the use of stabilizers also known as reamers, which are large cylindrical pieces of steel attached to the drill string, and made to perfectly fit the size of the hole being drilled. These have sets of rollers on the side, usually with tungsten buttons, that constantly break down cuttings being pushed upwards. The use of high-powered air compressors, which push 900-1150 cfm of air at 300-350 psi down the hole also ensures drilling of a deeper hole up to 1250 am due to higher air pressure which pushes all rock cuttings and any water to the surface. This, of course, is all dependent on the density and weight of the rock being drilled, and on how worn the drill bit is. Air core drilling and related methods use hardened steel or tungsten blades to bore a hole into unconsolidated ground. The drill bit has 3 blades arranged around the bit head, which cut the unconsolidated ground. The rods are hollow and contain an inner tube which sits inside the hollow outer rod barrel. The drill cuttings are removed by injection of compressed air into the hole via the annular area between the inner tube and the drill rod. The cuttings are then blown back to surface up the inner tube where they pass through the sample separating system and are collected if needed. Drilling continues with the addition of rods to the top of the drill string. Air core drilling can occasionally produce small chunks of cored rock. This method of drilling is used to drill the weathered regolith, as the drill rig and steel or tungsten blades cannot penetrate fresh rock. Where possible, air core drilling is preferred over RAB drilling as it provides a more representative sample. Air core drilling can achieve depths approaching 300 meters in good conditions. As the cuttings are removed inside the rods and are less prone to contamination compared to conventional drilling where the cuttings pass to the surface via outside return between the outside of the drill rod and the walls of the hole. This method is more costly and slower than RAB. Cable tool drilling. Cable tool rigs are a traditional way of drilling water wells. The majority of large-diameter water supply wells, especially deep wells completed in bedrock aquifers, were completed using this drilling method. Although this drilling method has largely been supplanted in recent years by other, faster drilling techniques, it is still the most practicable drilling method for large-diameter, deep bedrock wells, and in widespread use for small rural water supply wells. The impact of the drill bit fractures the rock and in many shale rock situations increases the water flow into a well over rotary. Also known as ballistic well drilling and sometimes called spudders, these rigs raise and drop a drill string with a heavy carbide-tipped drilling bit that chisels through the rock by finely pulverizing the subsurface materials. The drill string is composed of the upper drill rods, a set of jars, and the drill bit. During the drilling process, the drill string is periodically removed from the borehole and a baler is lowered to collect the drill cuttings. The baler is a bucket-like tool with a trapdoor in the base. If the borehole is dry, water is added so that the drill cuttings will flow into the baler. When lifted, the trapdoor closes and the cuttings are then raised and removed. Since the drill string must be raised and lowered to advance the boring, the casing is typically used to hold back upper soil materials and stabilize the borehole. Cable tool rigs are simpler and cheaper than similarly sized rotary rigs, although loud and very slow to operate. The world record cable tool well was drilled in New York to a depth of almost 12,000 feet. The common Bucera Series 22 can drill down to about 1,100 feet. Since cable tool drilling does not use air to eject the drilling chips like a rotary, instead using a cable-strung baler, technically there is no limitation on depth. Cable tool rigs now are nearly obsolete in the United States. They are mostly used in Africa or third world countries. Being slow, cable tool rig drilling means increased wages for drillers. In the United States, drilling wages would average around $200 per day per man, while in Africa it is only $6 per day per man, so a slow drilling machine can still be used in undeveloped countries with depressed wages. A cable tool rig can drill 25 feet to 60 feet of hard rock a day. A newer rotary drill cat top head rig equipped with down-the-hole hammer can drill 500 feet or more per day, depending on size and formation hardness. Reverse circulation drilling. RC drilling is similar to air core drilling, in that the drill cuttings are returned to surface inside the rods. The drilling mechanism is a pneumatic reciprocating piston known as a hammer driving a tungsten steel drill bit. RC drilling utilizes much larger rigs and machinery, and depths of up to 500 meters are routinely achieved. RC drilling ideally produces dry rock chips, as large air compressors dry the rock out ahead of the advancing drill bit. RC drilling is slower and costlier but achieves better penetration than AB or air core drilling. It is cheaper than diamond coring and is thus preferred for most mineral exploration work. Reverse circulation is achieved by blowing air down the rods, the differential pressure creating airlift of the water and cuttings up the inner tube, which is inside each rod. It reaches the diverter at the top of the hole, then moves through a sample hose which is attached to the top of the cyclone. The drill cuttings travel around the inside of the cyclone until they fall through an opening at the bottom and are collected in a sample bag. The most commonly used RC drill bits are 5-8 inches in diameter and have round tungsten buttons that protrude from the bit, which are required to drill through shale and abrasive rock. As the buttons wear down, drilling becomes slower and the rod string can potentially become bogged in the hole. This is a problem as trying to recover the rods may take hours and in some cases weeks. The rods and drill bits themselves are very expensive, often resulting in great cost to drilling companies when equipment is lost down the borehole. Most companies will regularly regrind the buttons on their drill bits in order to prevent this, and to speed up progress. Usually, when something is lost in the hole, it is not the drill string, but rather from the bit, hammer, or stabilizer to the bottom of the drill string. This is usually caused operator error, overstressed metal, or adverse drilling conditions causing downhole equipment to get stuck in a part of the hole. Although RC drilling is air-powered, water is also used to reduce dust, keep the drill bit cool, and assist in pushing cutting back upwards, but also when collaring a new hole. A mud called lick-ipol is mixed with water and pumped into the rod string, down the hole. This helps to bring up the sample to the surface by making the sand stick together. Occasionally, super foam is also used, to bring all the very fine cuttings to the surface, and to clean the hole. When the drill reaches hard rock, a collar is put down the hole around the rods, which is normally PVC piping. Occasionally the collar may be made from metal casing. Collaring a hole is needed to stop the walls from caving in and bogging the rod string at the top of the hole. Collars may be up to 60 meters deep, depending on the ground, although if drilling through hard rock a collar may not be necessary. Reverse circulation rig setups usually consist of a support vehicle, an auxiliary vehicle, as well as the rig itself. The support vehicle, normally a truck, holds diesel and water tanks for resupplying the rig. It also holds other supplies needed for maintenance on the rig. The auxiliary is a vehicle, carrying an auxiliary engine and a booster engine. These engines are connected to the rig by high-pressure air hoses. Although RC rigs have their own booster and compressor to generate air pressure, extra power is needed which usually isn't supplied by the rig due to lack of space for these large engines. Instead, the engines are mounted on the auxiliary vehicle. Compressors on an RC rig have an output of around 1000 CFM at 500 psi. Alternatively, standalone air compressors which have an output of 900-1150 CFM at 300 to 350 psi each are used in sets of 2, 3, or 4, which are all routed to the rig through a multi-valve manifold. Diamond core drilling. Diamond core drilling utilizes an annular diamond-impregnated drill bit attached to the end of hollow drill rods to cut a cylindrical core of solid rock. The diamonds used to make diamond core bits are a variety of sizes, fine to microfine industrial-grade diamonds, and the ratio of diamonds to metal used in the matrix affects the performance of the bit's cutting ability in different types of rock formations. The diamonds are set within a matrix of varying hardness, from brass to high-grade steel. Matrix hardness, diamond size and dosing can be varied according to the rock which must be cut. The bits made with hard steel with a low diamond count and are ideal for softer highly fractured rock, while others made of softer steels and high diamond ratio are good for coring in hard solid rock. Holes within the bit allow water to be delivered to the cutting face. This provides three essential functions: lubrication, cooling, and removal of drill cuttings from the hole. Diamond drilling is much slower than reverse circulation drilling due to the hardness of the ground being drilled. Drilling of 1200 to 1800 meters is common, and at these depths, ground is mainly hard rock. Techniques vary among drill operators and what the rig they are using is capable of. Some diamond rigs need to drill slowly to lengthen the life of drill bits and rods, which are very expensive and time-consuming to replace at extremely deep depths. As a diamond drill rig cores deeper and deeper, the time-consuming part of the process is not cutting 5 to 10 more feet of rock core but the retrieval of the core with the eye line and overshot tool. Core samples are retrieved via the use of a core tube, a hollow tube placed inside the rod string and pumped with water until it locks into the core barrel. As the core is drilled, the core barrel slides over the core as it is cut. An overshot attached to the end of the winch cable is lowered inside the rod string and locks onto the back end, located on the top end of the core barrel. The winch is retracted, pulling the core tube to the surface. The core does not drop out of the inside of the core tube when lifted because either a split ring core lifter or basket retainer allow the core to move into, but not back out of the tube. Once the core tube is removed from the hole, the core sample is then removed from the core tube and catalogued. The driller's assistant unscrews the back end off the core tube using tube wrenches, then each part of the tube is taken and the core is shaken out into core trays. The core is washed, measured and broken into smaller pieces using a hammer or sawn through to make it fit into the sample trays. Once catalogued, the core trays are retrieved by geologists who then analyze the core and determine if the drill site is a good location to expand future mining operations. Diamond rigs can also be part of a multi-combination rig. Multi-combination rigs are a dual setup rig capable of operating in either a reverse circulation and diamond drilling role. This is a common scenario where exploration drilling is being performed in a very isolated location. The rig is first set up to drill as an RC rig, and once the desired meters are drilled, the rig is set up for diamond drilling. This way the deeper meters of the hole can be drilled without moving the rig and waiting for a diamond rig to set up on the pad. Direct push rigs. Direct push technology includes several types of drilling rigs and drilling equipment which advances a drill string by pushing or hammering without rotating the drill string. While this does not meet the proper definition of drilling, it does achieve the same result as a borehole. Direct push rigs include both cone penetration testing rigs and direct push sampling rigs such as a power probe or geoprobe. Direct push rigs typically are limited to drilling in unconsolidated soil materials and very soft rock. CPT rigs advance specialized testing equipment, and soil samplers using large hydraulic rams. Most CPT rigs are heavily ballasted as a counter-force against the pushing force of the hydraulic rams, which are often rated up to 20 kN. Alternatively, small, light CPT rigs and offshore CPT rigs will use anchors such as screwed-in ground anchors to create the reactive force. In ideal conditions, CPT rigs can achieve production rates of up to 250 300 meters per day. Direct push drilling rigs use hydraulic cylinders and a hydraulic hammer in advancing a hollow core sampler to gather soil and groundwater samples. The speed and depth of penetration is largely dependent on the soil type, the size of the sampler, and the weight and power of the rig. Direct push techniques are generally limited to shallow soil sample recovery in unconsolidated soil materials. The advantage of direct push technology is that in the right soil type it can produce a large number of high-quality samples quickly and cheaply, generally from 50 to 75 meters per day. Rather than hammering, direct push can also be combined with sonic methods to increase drill efficiency. Hydraulic rotary drilling. Oil well drilling utilizes tricone roller, carbide-embedded, fixed-cutter diamond, or diamond-impregnated drill bits to wear away at the cutting face. This is preferred because there is no need to return intact samples to surface for assay, as the objective is to reach a formation containing oil or natural gas. Sizable machinery is used, enabling depths of several kilometers to be penetrated. Rotating hollow drill pipes carry down bentonite and borite-infused drilling muds to lubricate, cool, and clean the drilling bit, control downhole pressures, stabilize the wall of the borehole and remove drill cuttings. The mud travels back to the surface around the outside of the drill pipe, called the annulus. Examining rock chips extracted from the mud is known as mud logging. Another form of well logging is electronic and is frequently employed to evaluate the existence of possible oil and gas deposits in the borehole. This can take place while the well is being drilled, using measurement while drilling tools, or after drilling, by lowering measurement tools into the newly drilled hole. The rotary system of drilling was in general use in Texas in the early 1900s. It is a modification of one invented by Fauvel in 1845. And used in the early years of the oil industry in some of the oil-producing countries in Europe. Originally pressurized water was used instead of mud, and was almost useless in hard rock before the diamond cutting bit. The main breakthrough for rotary drilling came in 1901, when Anthony Francis Lucas combined the use of a steam-driven rig and of mud instead of water in the Spindletop discovery well. The drilling and production of oil and gas can pose a safety risk and a hazard to the environment from the ignition of the entrained gas causing dangerous fires and also from the risk of oil leakage polluting water, land and groundwater. For these reasons, redundant safety systems and highly trained personnel are required by law in all countries with significant production. Sonic drilling. A sonic drill head works by sending high-frequency resonant vibrations down the drill string to the drill bit, while the operator controls these frequencies to suit the specific conditions of the soil rock geology. Vibrations may also be generated within the drill head. The frequency is generally between 50 and 150 Hz and can be varied by the operator. Resonance magnifies the amplitude of the drill bit, which fluidizes the soil particles at the bit face, allowing for fast and easy penetration through most geological formations. An internal spring system isolates these vibrational forces from the rest of the drill rig. Limits of the technology. Drill technology has advanced steadily since the 19th century. However, there are several basic limiting factors which will determine the depth to which a borehole can be sunk. All holes must maintain outer diameter. The diameter of the hole must remain wider than the diameter of the rods, or the rods cannot turn in the hole and progress cannot continue. Friction caused by the drilling operation will tend to reduce the outside diameter of the drill bit. This applies to all drilling methods, except that in diamond core drilling the use of thinner rods and casing may permit the hole to continue. Casing is simply a hollow sheath which protects the hole against collapse during drilling, and is made of metal or PVC. Often diamond holes will start off at a large diameter, and when outside diameter is lost, thinner rods put down inside casing to continue, until finally the hole becomes too narrow. Alternatively, the hole can be reamed. This is the usual practice in oil well drilling, where the hole size is maintained down to the next casing point. For percussion techniques, the main limitation is air pressure. Air must be delivered to the piston at sufficient pressure to activate the reciprocating action, and in turn drive the head into the rock with sufficient strength to fracture and pulverize it. With depth, volume is added to the in-rod string, requiring larger compressors to achieve operational pressures. Secondly, groundwater is ubiquitous, and increases in pressure with depth in the ground. The air inside the rod string must be pressurized enough to overcome this water pressure at the bit face. Then, the air must be able to carry the rock fragments to surface. This is why depths in excess of 500 m for reverse circulation drilling are rarely achieved. because the cost is prohibitive and approaches the threshold at which diamond core drilling is more economic. Diamond drilling can routinely achieve depths in excess of 1200 m. In cases where money is no issue, extreme depths have been achieved, because there is no requirement to overcome water pressure. However, water circulation must be maintained to return the drill cuttings to surface, and more importantly to maintain cooling and lubrication of the cutting surface of the bit, while at the same time reduce friction on the steel walls of the rods turning against the rock walls of the hole. When water return is lost, the rods will vibrate. This is called rod chatter, and that will damage the drill rods, and crack the joints. Without sufficient lubrication and cooling, the matrix of the drill bit will soften. While diamond is the hardest substance known, at 10 on the Mohs hardness scale, it must remain firmly in the matrix to achieve cutting. Weight on bit. The force exerted on the cutting face of the bit by the drill rods in the hole above the bit, must also be monitored. A unique drilling operation in deep ocean water was named Project Mohs. Research of new drilling technologies. Research includes technologies based on the utilization of water jet, chemical plasma, hydrothermal spallation or laser. Utilization of high-energetic electrical plasma shows promise in deep drilling applications. This approach has potential to replace conventional drilling technologies. It would be able to produce boreholes with large constant diameter without frequent replacement of the drill bits. Causes of deviation. Most drill holes deviate slightly from their planned trajectory. This is because of the torque of the turning bit working against the cutting face, because of the flexibility of the steel rods and especially the screw joints, because of reaction to foliation and structure within the rock, and because of refraction as the bit moves into different rock layers of varying resistance. Additionally, inclined holes will tend to deviate upwards because the drill rods will lie against the bottom of the bore, causing the drill bit to be slightly inclined from true. It is because of deviation that drill holes must be surveyed if deviation will impact the usefulness of the information returned. Sometimes the surface location can be offset laterally to take advantage of the expected deviation tendency, so the bottom of the hole will end up near the desired location. Oil well drilling commonly uses a process of controlled deviation called directional drilling. Rig equipment. Drilling rigs typically include at least some of the following items. See drilling rig for a more detailed description. Blowout preventers. The equipment associated with a rig is to some extent dependent on the type of rig, but are devices installed at the wellhead to prevent fluids and gases from unintentionally escaping from the borehole. Number 23 is the annular and number 24 is the pipe rams and blind rams. In the place of number 24, variable bore rams or VBRs can be used. These offer the same pressure and sealing capacity found in standard pipe rams, while offering the versatility of sealing on various sizes of drill pipe, production tubing and casing without changing standard pipe rams. Normally VBRs are used when utilizing a tapered drill string. Centrifuge, an industrial version of the device that separates fine silt and sand from the drilling fluid. Solids control equipments for preparing drilling mud for the drilling rig. Chain tongs, wrench with a section of chain that wraps around whatever is being tightened or loosened. Similar to a pipe wrench. Dagger, a device that separates air and or gas from the drilling fluid. Desander/desilter, contains a set of hydrocyclones that separate sand and silt from the drilling fluid. Drawworks, is the mechanical section that contains the spool, whose main function is to reel in out the drill line to lower the traveling block. Drill bit, is a device attached to the end of the drill string that breaks apart the rock being drilled. It contains jets through which the drilling fluid exits. Drill pipe, joints of hollow tubing used to connect the surface equipment to the bottom hole assembly and acts as a conduit for the drilling fluid. In the diagram, these are stands of drill pipe which are 2 or 3 joints of drill pipe connected together and stood in the derrick vertically, usually to save time while tripping pipe. Elevators, a gripping device that is used to latch to the drill pipe or casing to facilitate the lowering or lifting into or out of the borehole. Mud motor, a hydraulically powered device positioned just above the drill bit used to spin the bit independently from the rest of the drill string. Mud pump, reciprocal type of pump used to circulate drilling fluid through the system. Mud tanks, often called mud pits, provides a reserve store of drilling fluid until it is required down the wellbore. Rotary table, rotates the drill string along with the attached tools and bit. Shale shaker, separates drill cuttings from the drilling fluid before it is pumped back down the borehole. See also: boring, flame jet drill, mineral exploration, oil platform, oil well, pump jack, subsea. References. External links: OSHA Guide for Drilling Rigs.